Today, we're going to pull back the curtain on what feels like a straight-up magic trick. How do you create a shared secret right out in the open without anyone snooping in ever figuring it out? We are talking about the Diffie-Hellman Key Exchange, and trust me, it's the elegant foundation for so much of our online security.
Okay, let's just jump right into the big puzzle. Imagine you and a friend can only talk to each other by sending postcards. Postcards that anyone, the mail carrier, your neighbor, anyone, can read. How in the world do you agree on a secret key that only the two of you know? It sounds totally impossible, right? But this exact problem gets solved millions of times a day, every single time you go online, all thanks to this brilliant idea.
So to really get our heads around this, let's forget about computers and code for just a minute. Instead, we're going to think about something way simpler, mixing paint. You'll see, this analogy is pretty much the perfect way to build an intuition for how this whole thing works.
Okay, follow along with me here. It all starts with a public color that everyone knows about. Let's say yellow. Then, you and your friend each secretly pick your own private color and mix it into the yellow. You swap these new mixes, your greenish mix and their orangey one, right out in the open. Now here comes the magic. You each take the mix you just got and you add your own original secret color one more time, and boom, look at that. You've both created the exact same final secret color, but you never actually sent it to each other. Anyone who is watching is just left scratching their head.
And that right there, that's the absolute core of it. Just think about it for a second. An eavesdropper saw the public yellow, they saw the green mix, and they saw the orange mix. But because they have no idea what your private colors were, they have no easy way to figure out how to get to that final secret brown color. The secret was never sent. It was created on both ends.
So that's the beautiful idea behind it all, right? But how do we translate this awesome paint mixing trick into the ones and zeros our computers actually understand? Well, that's where the real protocol comes in. We're swapping out paint cans for pure mathematics.
It's actually a pretty clean one-to-one translation. The public yellow paint, that becomes a set of public numbers or parameters that everyone can see. Your secret private color, that's your private key, a secret number you never ever share. The mixed paint you send across, that becomes a public value that you can transmit openly. And that final shared secret color that you both created, well, that's the shared secret key, ready to lock down your conversation.
Now this is a super important point to get. Diffie-Hellman's only job, its one and only job, is to do this digital paint mixing to create a shared key. It doesn't actually encrypt your emails or your messages itself. Its whole purpose is to securely agree on a key that some other, usually faster encryption method is going to use to do the actual locking and unlocking of your data. Think of it like the secret handshake you do before you start telling secrets.
But you're probably still thinking, wait a minute, if an attacker sees all the public numbers and the values being exchanged, what really stops them from just doing the math themselves and figuring it out? Great question. The answer lies in a really cool mathematical lock.
Yeah, this is the essential question, isn't it? It feels like there must be a flaw here. If all this info is public, why can't it be cracked? Well, the entire security of this whole system hangs on one surprisingly simple, real-world idea. The security really just hinges on this beautiful asymmetry. It's just like our paint analogy. It's super easy to mix blue and yellow paint to get green, right? But if I just hand you a bucket of that green paint and say, okay, now perfectly separate this back into the original blue and yellow, well, good luck. It's practically impossible. The math behind Diffie-Hellman is exactly the same. It's a one-way street. And there's an official term for this, computationally infeasible. Now, that doesn't mean it's logically impossible. It just means that even if you had every supercomputer on Earth working together on this one problem, it could take billions of years, longer than the age of the universe, to crack it. So, for all practical purposes, it's an unbreakable lock. Okay, so it's a clever mathematical trick. But where do we actually see this thing in action? As it turns out, this invisible agreement is one of the most critical building blocks of our entire modern digital world. You know that little padlock icon you see in your browser's address bar when you're on a secure website? Yep, that's very often Diffie-Hellman kicking things off. It's the engine running behind the scenes in secure messaging apps, protecting your private chats. It's what secures your connection when you use a VPN, and it's used in all sorts of secure file transfers. It's basically the internet's invisible security guard.
And really, that's the whole ballgame. Before Diffie-Hellman came along, everyone thought that to share a secret, you had to already have some kind of secure channel to send it on. This idea completely flipped that on its head. It was the first public key protocol that proved you could create a private secret on a completely public stage. It didn't just solve a puzzle, it literally built the bridge that allows for the private, secure internet we all rely on every day.
All right, so let's quickly boil it all down. What are the core pieces of magic we've just uncovered?
When you get right down to it, it's all about this. By using a clever one-way mathematical function, something easy to do but ridiculously hard to undo, we can create a shared secret right out in the open without ever having to risk sending it. And that simple foundational trick is what lets us build a whole world of private communication right on top of a very public internet.
You know, we started with what seemed like an impossible puzzle, and we found the answer hidden in a beautiful, elegant piece of mathematics. It kind of makes you wonder, doesn't it? What other huge challenges that seem like magic today are just waiting for the right mathematical key to come along and unlock them?